Good morning, students. Today we are going to see about the microwave spectroscopy, just in the spectroscopy, molecular spectroscopy. Yes. Later we are seeing about what is meant by before we are seeing about the what is meant by microwave spectroscopy. Sorry, what is meant by spectroscopy and what it deals with. Yes, it deals with the spectra of molecules, different kinds of molecules. Today we are going to see about the specialized one is microwave spectroscopy. From the name itself we can see. So we are going to use the microwave regional radiations for the study of spectra of molecules. Yes. So the spectroscopy in the microwave region is concerned. So today we are going to see about the rotation spectra, classification of molecules, rigid rotator, interaction of radiation with the rotating molecules, then how about its intensity of spectral lines and its applications. Okay. So what about this spectrum? This spectroscopy, it's kind of spectroscopy. This spectroscopy is concerned with the study of rotating molecules. Yes, the rotation of three-dimension body is very quite complex, and it is convenient. It is convenient to resolve into rotational components. Yes, and about the mutual in what way? About the mutually perpendicular directions through the center of gravity, that is called as principal axis of rotation. So it is very quite complex that we cannot able to study the three-dimension rotation of a body, but we are studying that as a rotational in three dimension as a components. Yes. So three mutual perpendicular directions x, y and z axis through the center of gravity, and this name is called as principal axis of rotation. Okay. So how it is mentioning, the body has three principal moments of inertia as IA, IB and IC. We are naming it as the axis. In each axis we are saying the moment of inertia as IA, IB and IC. Yes, here the molecules are classified into groups according to their relative values of their three principal moments. Yes, according to the relative values of their three principal moments of inertia, IA, IB and IC. Okay, so which is how we can say according to their we can be classified it. Yes. So to describe this classification, we have to see about the rotational spectra for each group. How it will be, how we have it will be. So we can see. First one is linear molecules. Yes, here the name implies that all the molecules of all the atoms are arranged in a straight line. Simple. They are arranged in a straight line. So such example is HCl. We can say H bond Cl, single bond Cl. Yes. Or we can say it is OCS, that sulfide. O, single bond C, single bond S. Yes, that is the direction of rotation takes place in which direction? About the bond axis, or at maybe end over end rotation in the plane of paper, and it may be end over end rotation right angles to the plane. Right angles to the plane. So here IA equal to 0 and IB is equal to IC. That's the main thing here. Here IA equal to 0 but IB equal to IC. Since why we are saying it is about the bond axis, the value is very small. Rotation value is very small. We cannot able to separate it. We cannot able to give the value. So IA is equal to 0. Here for linear molecules always IB equal to IC. Next type of classification is the symmetric tops. So what about the symmetric tops? Yes, consider a molecule such as methyl fluoride. Yes, symmetric top. Yes, consider a molecule such as methyl fluoride where three hydrogen atoms are bonded tetrahedrally. How? We can see here C, single bond H, single bond F. Yes, this is called a symmetric top, or otherwise we can say it here. And methyl fluoride, here we can see it is B here, and the single top Cl, and the bottom we are having Cl. Yes, here the three hydrogen atoms are bonded tetrahedrally to the carbon atoms. Yes, they are tetrahedrally arranged. As in the case of linear molecules, here we can say the moment of inertia As in the case of linear molecules, the end is here is out of plane of the paper and are still identical. They are both or equal. So we can say here IB equal to IC as here. But IA not equal to 0. That is the bond to the axis is not 0 because it involves a rotation about the 3 comparative massive hydrogen atoms. Yes, 3 hydrogen massive atoms. So here the symmetric tops always IB equal to IC but not equal to IA. Not equal to IA. So we can say it is a symmetric top. But here we are having sometimes we are having subdivisions. For example, this maybe boron trichloride will have a IA is equal to 2 IB, that is equal to 2 IC. Both sometimes there may be change in their molecule structure, that is called as prolate symmetric top, or we can say it is a oblate, or otherwise we can say some other names to the symmetric top molecules. Now we can next type of molecule is the spherical tops. Then how will be the spherical top? What about its structure? We can say the best example for the spherical core is tetrahedral molecules. Methane, tetrahedral. Yes, we can say here. When a molecule has a 3 moments of inertia identical, IA equal to, in the first linear, we IA equal to 0, IB equal to IC, but in symmetric tops, we have IA equal to IB, but IA not equal to 0, but IA not equal to IB or IC. In spherical top, these both 3 moment of inertias, IA equal to, IB equal to IC. So we can say this symmetric tops will be different one. Molecules 3 moments. The best example is the methane. Best example is the methane. Here the molecules have the symmetry rotation can how we can say this, the rotation cannot be observed easily because all are identical, so we cannot able to identify the rotation spectra. But in asymmetric top molecules, the majority of the substance have all the moments of inertia is different. IA not equal to IB, not equal to IC. The simple example are H2O, CH2 equal to, or otherwise we can say CHCl. All these are totally different. They are not correlated to each other. Okay. So these are the classifications about the rotational spectra. And these are some of the diagrams that is given for the bond diagrams for the different molecule classification of molecules. Then for rotational spectra, what are the requirements we can say? Okay, rotational molecular requirements. It should be the molecules should have a moment of inertia and having a rotational identity about the for the electromagnetic wave radiations. That is the main thing. The next we can see about which type of molecules does not show. Mainly homonuclear molecules, that is nitrogen, oxygen. There is no change in the dipole moment because the rotation takes place because of the dipole moment of the molecules. Always the moment of inertia will be very, very, very small for a homolinear and a linear diameter atomic molecule. So they do not have some rotational spectra. Next we can see about the techniques and instrumentation. That is the main part in microwave spectrometer. Here the techniques and instrumentation, we have the simple collimator. Then we can see about the always all these type of instruments. All these type of instruments always will have a collimator, then a specimen, and the light will be falling on the spectrum sample what we need the molecules to be analyzed, and these are the techniques. Here we are having a see, we can see the simple one. This is the main schematic diagram of a microwave spectrometer. Here the source is the klystron bulb is a monochromatic source, emits radiation over only a few narrow frequency range, and it is passed through this mica window. Why? Because to be narrow path light has to be passed, and the beam direction should be guided, so we are using as a waveguides. Okay, and the radiation will be passed on to the sample. Before that, all these experiments to be started, the main area should be vacuumed. Because of this, if there is a pressure presence inside the chambers, what happens is the molecule due to the disturbances. So it should be so it should be control. So it should be controlled. For this, we need a vacuum. Yes. Then again, when the light from microwave region falls on the sample and it is detected by a detector. Yes. So what detector here can be used? Many type of detectors can be used nowadays. We are using a simple radio receiver as a detector. That is the main where it detects the radiation focused on it as a waveguide, and the signal it gives the amplified, and it is this amplification has been seen through displayed on an oscilloscope for a permanent record on a paper. The sample space is always a gaseous, always, so it should be evacuated, and that is the main thing, and it should be around 10 power minus 4 to 10 power minus 5 mm of mercury. The vacuum should be maintained. So this is the main instrumentation area. Okay, so mostly these microwave molecules can be gives the rotation spectra of the molecules. That's the main thing we needed. From this only we can say whether it is classified in the linear or top or symmetric tops, or otherwise we cannot able to find it out by some other analysis. Okay, in the next class we can see about the rotation spectra of a diatomic molecules, how it is behaving. Okay. Thank you students.